this very simple object, a plane using pictures, so I'll try to do that. And in addition, I'll also try to, and so I'd like constructions. Good. Okay, got fancy animations. Good. All right, so as all of you know, and how? Well, primarily by borrowing tools from computational complexity, extraordinary progress in better understanding how succinct arguments can be constructed, in particular using PCPs, commitment schemes. Great, so like maybe about half popular. And so people were constructing succinct arguments kind of like that, using like clever tricks. It wasn't clear what was happening, okay? And back then, so we've seen that this paradigm was extremely successful, okay? Kind of some polynomial PCP, and then you have something coming from crypto, okay? Is your verifier going to be succinct or not? This is come on top of the probabilistic proof, okay? Some they're substantial, okay? Use the resulting succinct argument may be pre or post discrete logarithm on the hardness of the discrete logarithm problem, then of course the resulting succinct argument randomness, or is it a private coin setup where you may have to rely on a ceremony? That's determined by the crypto that you use, okay? In some sense, by definition, no structure at all, okay? So ideal hash functions, okay? There is, all right. So before we get to how do we build, the main difference is different types of probabilistic proofs, okay? So I like to use this term probabilistic proof. So, so here are kind of four notions of round complexity. So interaction, can you forth or can you go and talk across multiple rounds? Of course, random. And oracle access. Oracle access simply means that the prover will access them as strings to be read that may have, for example, some special access by the ability to potentially read like one symbol at a time, okay? Depending upon how you mix and match the notion of an interactive proof that lets the verifier use randomness and interact with interactive proofs. If it's this message, by reading kind of specific locations of it using queries, okay, you kind of have proven interactive oracle proof, okay? And these probabilistic proofs play different roles. Which symbol you want to read, and you say, I want to read location 3, here's the answer, I want to read location. So you treat the string as a polynomial, and each query says at which point. Interactive proofs primarily serve as subroutines. Most notably, the sum check are really efficient, so we mostly use them as research or for teaching, because themselves are not really efficient. Provers within like a single prover, okay? Like heavy cryptography. The type of probabilistic proof, any questions? Okay. Again, when I say any questions, it's not rhetorical. I really mean, like, if you have a question, please like raise your hand and I'll answer. Okay. All right, so I said that today I want to tell you about succinct arguments from hash functions, specifically ideal hash functions, so let's briefly talk about them, okay? So a cryptographic hash function is an algorithm that maps an arbitrary length input to some output of a certain size, the size being, let's say, the security parameter, okay? And hash functions in the real world are designed to have no useful structure, okay? They're even though we try to design them with no useful structure, it's kind of pretty hard to say, okay, this is the list of properties. So usually when you analyze schemes with, for example, SHA-256, you're going to try to model it as if it literally has no structure, namely it is a random function, okay? So this leads to something that the cryptographers call the random oracle model, where every party, this includes honest and malicious parties, have query access to a randomly sampled function, okay? And so now you're inside, so of course this is not reality. In the real world we don't have a random function, but we think that hash functions we do design can be reasonably assumed to behave like random functions. So the kind of theorems that you try to prove in the random oracle model have this flavor. You say, look, let's fix some adversary, and let's bound the number of queries that it can make to the oracle. The bound is t, okay? So think about this as the size of the adversary. And then you want to prove that the probability over the choice of hash function that the adversary breaks your scheme is bounded by some function of the resources of the adversary, so that the bound on the number of queries t, and the security parameter lambda, which is the output size of your hash function. Okay? So this is kind of the picture. You have your adversary. It interacts with the hash function over some number of times, and up to t times, and it tries to break your scheme. All right? Good. All right, so it is in this model, in the random oracle model, that we can construct succinct arguments. And today I want to tell you about how one does it and what are their security properties. I also want to kind of take a step back for a moment and just point out, and so that we can appreciate how amazing it is that we can construct succinct arguments just from random oracles. There are all kinds of goals in cryptography that we know for a fact we cannot construct purely from random oracles. For example, non-interactive key agreement, something like a Diffie-Hellman kind of key exchange, which we can do with number theory. We know we cannot do purely from random oracles. Okay, so there are a number of natural, let's say, public key cryptography type of goals that we need some structure from nature, whether it comes from lattices or from number theory, whatever, to achieve these goals. But a succinct argument, that's like incredibly powerful primitive. Like it's basically like lets you create a little hash for a long computation that you can check exponentially faster than the computation itself. And all you need is just some random function. That's it. Okay? You don't need anything else. That's pretty amazing. Okay? Usually advanced crypto needs kind of like advanced assumptions or advanced structure. Okay? This is something where you don't need that. Okay? And it's wonderful. Okay? Also, it's not just wonderful, but it's safe, okay? One way or the other, we will always have some hash functions, okay? It's kind of like if hash functions fall, then all of crypto falls. Yeah, please. Yeah. Yeah, let me talk a little bit about, so, yeah, so yes. So the question was about the programmable random oracle model and, how is it realistic? And so, in the random oracle model, your adversary issues queries to an oracle. In particular, when you try to prove a scheme secure in this model, your security reduction may have certain privileges, and these privileges are there because you're in an idealized world, whereas in the real world, these privileges may not be there, okay? Here's an example. In a security reduction, and this is actually something that succinct arguments do rely upon, and is you can observe the queries from the adversaries to the random oracle and use the information of these queries, for example, to prove soundness of a succinct argument, okay? Observing the queries to the random oracle, this is something known as kind of observability of the random oracle, okay? And it is essential for security. And this is why, for example, once you instantiate the random oracle as SHA-256, you can no longer kind of see specific queries in an arbitrary adversary. You're really only making a heuristic step from the analysis in the random oracle model to the real world. For some properties, you may need even yet other, maybe more exotic features. For example, to prove that a succinct argument is zero knowledge, okay? You have to, and one can prove it's necessary, program the random oracle. So basically, your simulator for zero knowledge has the extra power to choose the answers that the hash function will give to certain queries, okay? And this is kind of a byproduct of working in an idealized model, and we can, I can get into maybe more kind of technical details for why these are kind of reasonable enough things to do, but kind of when you work in an idealized model, your proof techniques are necessarily going to be like not in the real world, they're going to be in like the idealized model. More generally, as you know, like everything that involves succinct non-interactive arguments must use some sort of non-standard things, whether it is the random oracle model, knowledge assumptions, because we cannot construct these things from so-called falsifiable assumptions. There are like limitations on snarks. Yeah, thank you. More questions? Good. I'll come back to some of these things in a moment, specifically like observing the random oracle. Okay, so even though in general the construction succinct argument may look complicated, there are some constructions that are exceedingly simple and intuitive. Some right now. They're very beautiful, very easy to explain. Okay, so specifically, if we kind of put aside happy to work with PCPs, going from a PCP to a succinct argument is very simple. Okay, so has oracle access to a single prover message. Okay, so here how it looks, and as a regular message, the MP witness is kind of written somewhere. Think about it in the sky, and the verifier can just there. The verifier can not only can make a small number of queries, but can also run in a small amount of time, much smaller than the proof. In this model, an order, you write down the PCP, then the queries are sampled. So proof, I send the queries to the prover, and the prover tells me the answers. I see some people nodding yes, some people nodding no. So this is not okay, because on most PCPs of interest, there are some answers that will make the verifier answers have been fixed, then the queries are sampled, right? So it's kind of like the prover has to commit to the PCP in advance, and then the cryptography comes in. Cryptography will come in to help the prover. Okay, this was the Killian's protocol, the first succinct argument design, and to this day remains the simple functions called a Merkle tree. Okay, I'm sure most of you have seen Merkle trees before. To take a long string, pairwise hash it down into a single root so that you can then reveal parts of the long string without revealing the entire string. Okay? So that it runs the PCP prover, it produces the PCP string, but because it will say, okay, let me just commit to it using a Merkle tree, and I will send to the argument verifier just the root of the tree. So it says, look, here's my randomness. Please figure out which queries I'm going to see with this randomness. And here's an opening proof that I can send you that certifies the answers. You can check the and then you can check that indeed the PCB verifier is happy with it. Okay? So basically, cryptography can provide a commitment with the property that you can commit to long strings and have kind of succinct openings to just the part of the string that you want to read. Okay? That's it. This is the simplest succinct argument out there. It's a beautiful idea, and it really needs no fancy crypto. It's just like hash functions. Okay? Questions? Good. So let's just observe some things. First, the crypto here, unlike other succinct arguments, is very. So if you look at the time of the prover and the verifier, they are basically the time of the prover and verifier for the underlying PCP plus hash. Of course, if the PCP sucks, then your succinct argument is also going to suck. Okay, but the crypto is not to blame. All right, you're just adding a few hashes on top. That's great. The other point is that the entire PCP, now all you sent was a little hash for the root, that's like lambda bits, and then the query's answers and proof. And if you remember, in a Merkle tree, of digests from that location to the root, so that's logarithmic in the length of the PCP. So you have some. Think about it as just number of queries, okay, to a first order. So essentially, we is this world where your communication complexity in a succinct argument is basically query complexity of the underlying PCP. And finally, this is something I want to spend the next 10, 15 minutes on. Security, okay? So one can prove that the probability that, let's look at the soundness property for now. Queries to random oracle convinces a verifier to accept an instance not in the language is bounded by two terms. One term, of course, PCP has a bad sound, etc. We're going to incur it, right? But then, you know, we're not just running a PCP. Circle tree, intuitively, you can break using collisions. Okay, so you have some sort of collision type bound type behavior, right? Where kind of finding collisions is much easier than inverting, right? Kind of your success probability grows with the square of the number of queries you make. And okay, so that's intuitive, that's great. If you want the success probability of like a big adversary to break your scheme to be just half, then you can say, okay, I'll make the PCP have soundness error a quarter. That's well, you know, if the adversary makes at most 2 to the 128 queries, that means that the put that, you know, and another, you know, factor of 4, right? So extremely transparent and easy to understand kind of construction whose security is also pretty clear. Okay? Questions?
Is it that instead of the two very powerful adversary chance of failing with half, we instead have a weak adversary? I guess those two are two different ways of formulating the problem. Why are you choosing this approach?
Yeah, this is just, you know, one point. Once you have the expression, you can sort of pick parameters so that if the adversary is just mid-size, then it has an extremely small probability. Intuitively, one goal is you want the ratio between the resources of adversary and the success probability to always, right? Because that's kind of the expected work that it's going to put in, right? Like if with probability, if having in expectation to actually succeed, you're going to pay work T over epsilon, right? So you want that thing to be large, okay? Change it slightly to achieve that. Right? Yeah, good question. Now, here is that this is like the simplest one. What we use in practice is not this construction. First, it's interactive, and second, it uses PCPs. And setting the security of things in practice. But even though it's less obvious, it doesn't mean that it's not easy to understand, okay? And I promise we can do it in just like 10 minutes. It's actually really not that complicated. Such argument, whereas in reality, we're primarily interested in succeeding to the second Succinct argument in this talk, and also the second one in history. Okay, so shortly after Killian published his paper, Silvio Micali observed that in the random oracle model, you can make it non. You're going to use the Fiat-Shamir transformation onto Killian's protocol. So the idea is that you start the same way. Sending it, you stick it back in the random oracle, and you get back out some randomness, as if the verifier would have sent it to you. Okay? And now you fire and do the same thing as before, and now you send the first and second message of the prover in Killian's argument in replicate it. It will say, look, yeah, I wasn't there, but I know how the prover was supposed to kind of derive it, so I will derive it the same way myself. See the same way as in Killian's protocol. Very small diff. Okay? But even though there is a small diff, the security behavior of this protocol is. Just repeat okay.
Remember to include X in the input to F, because that's a mistake that.
If you're Shamir, you always include the description of your instance, and if you rely. Okay, now the security has changed dramatically. Okay, so prover can kind of say, you know what? I don't like it. Why I don't like it? Because I didn't convince the verifier. Let me try again. So it goes back and says, oh, I tried this PCP and worses. But it does mean it's as if I get to interact with the Killian verifier many times. Okay? How many times? We're not too many. Be t times that, because it's you get potentially the chance, right? So this means that in this protocol, the PCP, like for the same success probability, the PCP has to be far more secure in Micali than it was in Killian. Non-interactive, but also the security changes. Very important to kind of understand, okay? Nevertheless, this can be understood. Micali protocol is not used. But otherwise, if it wasn't for that, it is an amazing protocol, and everybody would use it, okay? All right, so we're kind of past the hard part. Now in practice, we don't use PCPs. They are just PCPs across multiple rounds. So says, okay, thank you. I'll keep it around. But here's some randomness. Please send me another PCP. Here's that PCP system. And they are, by virtue of use, succinct arguments from IOPs. And IOPs today underlie essentially all modern. So this should be like pretty clear what an IOP is, right? So once we see an IOP, we say, okay, great. I know how to. If before I could just commit to a PCP string with a Merkle tree, then open, right? For each round, okay? So this protocol is used, like in every construction of a hash page. Picture-wise, it's pretty simple. Output the first PCP, commit to it, sample random questions, right? It's just the same paradigm, okay? Just say, forget interactivity for a moment. Let's just kind of make sure that we understand how to use Merkle trees across multiple rounds, okay? Instead of receiving, and it's because of the IOP, not the crypto, okay? Again, this is non-trivial. Like some other constructions of succinct arguments, the crypto expect to happen does happen. The security of the succinct interactive argument is the security of the IOP. But now things get complicated, all right? Yeah.
Is that the round-by-round security of the IOP?
Well, I'm getting to it now.
Oh.
So, like in the interactive, pay for is the error of the Merkle tree.
Yeah, it's only when you apply Fiat-Shamir.
Yeah, now we apply Fiat-Shamir and things start getting pretty practical and non-interactive. So we want to use IOPs, but also we don't want to have the interaction associated to them, okay? So this leads to the hash chain to produce the next message that will produce the next PCP feedback multi-round Fiat-Shamir, okay? And this leads to, all right? So again, a small diff is the construction that you would use in practice. Okay? Questions about it? Yeah, back there.
Random oracle models.
Great question. So interactively, adversary to the random oracle, you rely on a proof technique called rewinding, where you, after using a Merkle tree based on a collision-resistant hash function, we was thinking about. Okay? One can do it, and yeah. In the non-interactive setting, you need something, all right? So either some kind of extractable Merkle tree, or in particular, the protocol as shown in the previous slides, improve it. Thank you. Okay, so this is the BCS protocol, and what is the security? Well, we've used Fiat-Shamir to select the one it likes the most. So, for example, send you, this PCP, and then you send me this randomness. Now, in the BCS protocol, that means that you're going to have a different route. You get a different randomness, right? Different interaction. And you can also mix and match. You can say, look, I'm going to start the same as my first interaction, but then I'm interaction, you can kind of recover a prior state and fork from there, all right? Soundness is basically how the this is that I usually talk about, right? Usually you think of soundness as a one-shot into IOPs, or in general, interactive proofs, okay? Where if you rewind and you allow the prover to do the state translation, there are things called like special soundness or round-bound. The state translation soundness of the IOP with such strong soundness properties interactive protocols. Like you cannot really exploit the fact that they have many rounds to, because it could be that this entire picture would have failed precisely because status attacks. Okay? Yeah, and so in fact, if you, this kind of like the point that I wanted to get to, all right, that there's soundness error. But we're fortunate in that IOPs that we care about have excellent are pathological. Okay, so I'm about to, any questions?
Accumulator. Can we switch the Merkle tree with an accumulator in all of these schemes? Yeah. Why do we?
I mentioned that you can use a Merkle tree based on, can be constructed either from hash functions, you can construct them from pairings, you can also construct them from lattice, and then later open, so that openings, you know, you cannot kind of inconsistent openings. Things get more complicated in a non-interactive setting, okay? Because there, it's exactly what those properties are. Probably position binding is enough, okay? Of course, your security...
Them is there some intuition between, so about one is T times the original soundness the best?
Yes. T times epsilon is also lower bound. You can prove that, you know, it's at least that, okay? So you must, okay? In every round, the verifier sends a single bit. So it's like random bit, random bit, random bit. And at the end, small soundness error, right? The soundness error is like 2 to the minus number of rounds, okay? If you apply PHME, you're done, right? And now you can choose on the second one, and that's it, right? So one of the security notions that imply security under PHME is round by round soundness. That says that so you cannot do such things, okay? Great question. Okay, I'm gonna jump to the kind of conclusion slide, and I cannot jump because I mean. Okay, so this is my conclusion. So these are topics that I love very much. I find them in practice, to the point that actually I'm happy to announce that a few weeks ago, Elon, who is here, and 2.5, 3 years kind of systematizing, digesting, and the random oracle model, okay? So, so it's, snarks and so in the interactive world, we explained the Killian and the classical one-round and multi-round PHME, as well as how you combine both of these ideas to get the Mikali construction and BCS construction, okay? Dozens of papers, many of which are on these subjects, but still in this book, and there were like a number of details and kind of things that were, because these things are used in practice and they're like underlying real-world systems. We have an entire part just discussing commitment schemes in a random oracle model, like Merkle trees. We also have a whole this Merkle tree optimizations. How does wraparound soundness and special soundness imply good state restoration soundness? Not just the PDF, but also the source code, the LaTeX code. And it's available for free. Commons license. And yeah, so like we kind of spent a lot of time and we think it is, but if you have comments, or especially if you find any,
Any more questions?
Here.
Does the book cover your more recent work?
We take probabilistic proofs as a given, so we don't open them up. Falls from the sky, it's a PCP or an IOP. Whichever it is, then we compile it, and we tell you how to compile it, okay? What is inside the probabilistic proof, we don't say. I teach a course on probabilistic proofs alone, without any of this, and that's a different, kind of times, all the lectures and homeworks are online, and you can learn about the insides of probabilistic proofs. But we try to kind of draw a line and say, look, on my lap, now I want to compile any number theory or complexity even. Right? Yeah.
Let's thank the speaker once more. Thank you, Ale.